What if I told you there are places in the universe where reality itself is stretched and twisted beyond recognition? Welcome to the mind-bending world of black holes. These cosmic enigmas hold secrets that could transform our understanding of space, time, and everything in between. Today, we're diving into the 20 unknowns about black holes that will leave you questioning everything you thought you knew about the universe. Stay with us until the end, because each mystery we uncover will get stranger and more fascinating, from the way black holes bend light to the possibility of them being gateways to other dimensions. We'll explore the science, the theories, and the unimaginable wonders that make black holes the ultimate cosmic puzzle. So fasten your seatbelts, because the journey into the unknown starts now. The first unknown involves the true nature of singularity. Let's dive into this mind-bending concept that sits at the heart of every black hole. Imagine a point in space where gravity becomes so intense that it crushes everything into an infinitely small, infinitely dense point. That's a singularity. It's a place where our current understanding of physics just breaks down. You see, in a singularity, the usual rules of space and time cease to exist as we know them. It's like trying to solve a puzzle with pieces that don't fit together. Scientists believe that the singularity is so dense that it creates a gravitational pull that nothing can escape, not even light. But here's the crazy part: because we can't see it, we can't fully understand what's happening there. It's like trying to peek into a room with no lights and no windows. The singularity is wrapped in mystery, leaving us to wonder what really happens when everything collapses into one unimaginably small point. Some theories even suggest that singularities could be gateways to other parts of the universe, or even other universes altogether. But until we develop the tools to peek inside these cosmic enigmas, the singularity will remain one of the most baffling and intriguing mysteries of black holes. The second unknown involves what happens beyond the event horizon. The event horizon is often described as the point of no return. Once you cross it, there's no coming back. The event horizon is the invisible boundary surrounding a black hole where the gravitational pull becomes so strong that not even light can escape its grasp. But what actually happens beyond this mysterious line? One popular theory suggests that as you approach the event horizon, time starts to slow down relative to an outside observer. This means that if you were watching someone fall into a black hole, it would look like they were moving slower and slower, eventually freezing in time at the edge of the event horizon. However, for the person falling in, time would seem to continue normally. It's almost like stepping into a different dimension altogether. Once you cross the event horizon, all bets are off. Theories range from being stretched and compressed by the immense gravitational forces, a process somewhat morbidly referred to as spaghettification, to entering a new realm governed by different laws of physics. Pop culture has taken this concept and run wild with it. In movies like Interstellar, crossing the event horizon leads to mind-bending experiences where time and space are warped beyond recognition. Books and TV shows often depict the event horizon as a gateway to other worlds or dimensions, tapping into our fascination with the unknown. Despite all these theories and imaginative ideas, the true nature of what happens beyond the event horizon remains one of the greatest mysteries in astrophysics. Until we find a way to observe or measure these phenomena directly, this cosmic enigma will keep both scientists and storytellers up at night, pondering the infinite possibilities that lie beyond that ultimate boundary. The third unknown involves whether black holes can lead to other universes. Imagine for a moment that black holes are not just destructive forces, but could actually serve as portals to entirely different universes. This mind-blowing idea stems from theories in both quantum mechanics and general relativity. According to some scientists, the immense gravitational forces at the core of a black hole could warp space-time so extremely that a bridge or tunnel, known as a wormhole, may be created. This hypothetical tunnel could connect our universe to a completely different one on the other side. Think of it like a shortcut in a video game that transports you to an entirely new level. Fascinatingly, this theory raises the possibility that every black hole could be a gateway to a different universe, each with its own unique laws of physics and realities. One of the most captivating aspects of this idea is that it aligns with the concept of the multiverse, where multiple universes exist parallel to each other, each with its own version of reality. If true, black holes could be the very keys to accessing these parallel worlds. But before we get too carried away, it's important to note that these ideas are still largely theoretical. We currently lack the technology and means to test or observe these phenomena directly. Yet, the allure of black holes serving as cosmic doorways continues to captivate the imagination of scientists and science fiction enthusiasts alike. The thought that plunging into a black hole might not mean an end but a new beginning in a different universe is as exhilarating as it is perplexing. Until we can gather more concrete evidence, the notion of black holes as portals will remain one of the most tantalizing mysteries in the cosmos, provoking wonder and speculation about the true nature of our universe and what lies beyond. The fourth unknown involves the origin of supermassive black holes. Imagine trying to understand how these colossal giants, millions or even billions of times the mass of our Sun, come into existence. It's a puzzle that has baffled scientists for decades. One leading theory suggests that supermassive black holes form from the collapse of massive clouds of gas in the early universe. These gas clouds could have been dense enough to collapse directly into a black hole without first forming a star. Another idea is that they might have started as smaller black holes that merged over time, gradually growing larger by swallowing up stars, gas, and even other black holes. However, there's also the possibility that supermassive black holes grew from primordial black holes, which are thought to have formed in the chaotic aftermath of the Big Bang. These early black holes could have served as seeds, around which matter gathered and grew to form the supermassive black holes we observe today. The mystery deepens when we consider that supermassive black holes have been found at the centers of nearly all large galaxies, including our own Milky Way. How did these behemoths end up in such central and influential positions in the cosmos, and how did they grow so large so quickly in the early universe? Current research is pointing towards a mix of rapid early formation and continuous growth through mergers and accretion. But until we have more detailed observations and data, the exact process of how supermassive black holes come to be will remain one of the greatest enigmas in astrophysics. Scientists are using powerful telescopes and simulations to peel back the layers of this cosmic mystery. But for now, the origin of supermassive black holes continues to intrigue and mystify, offering a tantalizing glimpse into the violent and dynamic processes that shape our universe. The fifth unknown involves the role of black holes in galaxy formation. Black holes, particularly the supermassive ones at the centers of galaxies, are not just passive observers in the universe. They may actually play a significant role in shaping the structure and evolution of galaxies themselves. One compelling theory is that these supermassive black holes act like cosmic architects, influencing the formation and growth of galaxies around them. The intense gravitational pull of a black hole could regulate the flow of gas and stars within the galaxy, essentially dictating the galaxy's shape and dynamics. This relationship between a black hole and its host galaxy is so intimate that scientists even refer to it as co-evolution, suggesting that the growth of a galaxy and its central black hole are interconnected processes. Observations have shown that the mass of a supermassive black hole is often proportional to the mass of the galaxy's central bulge, implying a deep connection between them. Another intriguing aspect is how black holes can influence star formation. The energy released by a feeding black hole, known as active galactic nuclei, can either trigger new star formation by compressing nearby gas clouds or quench it by heating the gas and preventing it from collapsing into stars. This dual role makes black holes both creators and destroyers within their galactic realms. Furthermore, black holes might also be responsible for the mysterious shapes of galaxies. For example, the powerful jets emitted by a supermassive black hole can blow material out of the galaxy, shaping it into an elliptical form, while a less active black hole might allow for the development of a spiral structure. Essentially, black holes could be the hidden sculptors behind the diverse array of galaxy shapes we observe in the universe. Despite these fascinating insights, much about the role of black holes in galaxy formation remains speculative. We are just beginning to unravel the complex interplay between these cosmic titans and their galactic hosts. With advanced telescopes and simulations, scientists are getting closer to understanding how black holes influence the grand tapestry of the cosmos. The idea that black holes could be central to galaxy formation adds another layer of wonder and complexity to these already enigmatic objects, deepening our appreciation for their role in the universe. As we continue to explore and discover, the connection between black holes and galaxies will undoubtedly reveal more secrets, further illuminating the magnificent and mysterious dance of the cosmos. The sixth unknown involves whether black holes evaporate. Picture a black hole as an indestructible gravitational force pulling everything into its depths. But what if I told you that black holes might actually lose mass over time and eventually evaporate? This mind-boggling concept was introduced by physicist Stephen Hawking in 1974, leading to what is now known as Hawking radiation. According to Hawking, black holes are not entirely black. Instead, they emit a faint glow of radiation. This radiation arises from the quantum effects near the event horizon, where particle-antiparticle pairs are constantly being created. Normally, these pairs would annihilate each other, but sometimes one particle falls into the black hole while the other escapes. The escaping particle takes energy away from the black hole, causing it to lose mass slowly. Over an incredibly long time scale, this process could result in the complete evaporation of the black hole. Hawking radiation was a groundbreaking idea because it united quantum mechanics and general relativity, two of the most important theories in physics. However, it also sparked intense debate and further questions. For instance, what happens to the information that falls into a black hole? According to the rules of quantum mechanics, information cannot be destroyed, but if a black hole evaporates, what becomes of the information it absorbed? This conundrum is known as the black hole information paradox, and it remains one of the most significant unresolved issues in theoretical physics. Scientists are still striving to understand the full implications of Hawking radiation and whether black holes truly evaporate. Observing this phenomenon directly is incredibly challenging because the radiation is so weak and faint. Yet, the possibility that black holes could vanish over time adds an entirely new dimension to our understanding of these enigmatic objects. If Hawking radiation is confirmed, it could lead to groundbreaking insights into the nature of black holes and the fundamental laws of the universe. This ongoing debate captures the essence of scientific exploration, pushing the boundaries of what's known to uncover the mysteries that lie beyond. As we continue to investigate, the question of whether black holes evaporate will remain a tantalizing mystery, beckoning us to delve deeper into the enigmatic workings of the cosmos. The seventh unknown involves the possibility of mini black holes. Imagine black holes not as the massive cosmic giants we usually think of, but as tiny, microscopic entities that could fit on the head of a pin. This intriguing concept suggests that mini black holes could have formed in the early universe during the Big Bang. These primordial black holes would be incredibly small, with masses much less than that of a normal black hole, potentially even smaller than a grain of sand. Despite their tiny size, they would still possess immense gravitational pull, enough to warp space-time around them. One of the most fascinating implications of mini black holes is their potential to help us understand fundamental physics. If they exist, studying them could provide valuable insights into quantum gravity, a field that aims to reconcile general relativity and quantum mechanics. These tiny black holes could serve as natural laboratories, offering clues about how gravity operates on the smallest scales. Another exciting possibility is that mini black holes could be detected by high-energy particle collisions, like those produced in the Large Hadron Collider. If particle collisions generate mini black holes, it would not only confirm their existence but also open up new avenues for exploring the fabric of space-time. However, the formation and detection of mini black holes remain highly speculative. Scientists have yet to find concrete evidence of their existence, and the search is ongoing. If mini black holes are ever discovered, they could revolutionize our understanding of the universe, offering a glimpse into the very origins of space and time. The idea that black holes, whether colossal or minuscule, can exist in such diverse forms adds another layer of wonder to these cosmic mysteries, reminding us of the vast and varied nature of our universe. Until we find definitive proof, the possibility of mini black holes will continue to captivate our imagination, challenging us to uncover more about the enigmatic workings of the cosmos. The eighth unknown involves time dilation near black holes. Picture this: as you get closer to a black hole, time itself begins to behave in the most peculiar way. Time dilation is a mind-bending effect predicted by Einstein's theory of general relativity, which states that the stronger the gravitational pull, the slower time ticks. Imagine you're on a space adventure heading towards a black hole. As you approach, you would notice that your clock ticks more slowly compared to someone far away from the black hole. If you were to hover just outside the event horizon, the effect would become even more dramatic. To an outside observer, it would appear as if you were moving in slow motion. Minutes could pass for you, while years could fly by for someone far from the black hole. It's almost as if you're entering a different time zone where the rules of time become incredibly flexible. This phenomenon opens up some tantalizing possibilities. For example, if you could travel close to a black hole and return, you might find that everyone you knew had aged significantly while you experienced just a short period. It's like experiencing a form of time travel, albeit with the immense dangers of a black hole's gravitational pull. Some scientists even speculate that if you could harness this time-dilating effect, it could have practical applications in the future. However, the extreme conditions near a black hole make it nearly impossible to test these ideas with our current technology. Despite its speculative nature, the concept of time dilation near a black hole adds a layer of wonder and fascination to these cosmic enigmas. It challenges our conventional understanding of time, pushing us to imagine the unimaginable and ponder the mysteries that lie deep within the fabric of space-time. As we continue to explore and study black holes, the phenomenon of time dilation will remain one of the most captivating and perplexing aspects, a testament to the ever-intriguing nature of our universe. The ninth unknown involves the information paradox. This perplexing conflict in physics questions whether information that falls into a black hole is lost forever. According to the principles of quantum mechanics, information cannot be destroyed. However, if material falls into a black hole and the black hole eventually evaporates through Hawking radiation, what happens to the information contained in that material? This is the crux of the information paradox, which has puzzled scientists for decades. Imagine you throw a book into a black hole. The book, with all its intricate information, seemingly disappears from the universe. Classical physics would suggest that this information is lost forever within the black hole, but quantum mechanics insists that information must be preserved. This clash between general relativity and quantum mechanics creates a deep conundrum. One proposed solution to the paradox is that the information is somehow encoded in the Hawking radiation emitted as the black hole evaporates. However, this idea is still highly controversial and not fully understood. Another theory suggests that the information could be stored at the event horizon in a two-dimensional form, a concept known as the holographic principle. This principle implies that all the information contained within a three-dimensional space can be represented on a two-dimensional surface like a hologram. If true, it could mean that the surface of the event horizon holds all the information about the particles that have fallen into the black hole. Yet another idea involves the concept of black hole complementarity, which posits that information is both reflected at the event horizon and passes through it depending on the observer's perspective. This means that from one viewpoint, information is never lost because it's reflected back into the universe, but from another, it enters the black hole and is somehow preserved inside. Despite these intriguing theories, none of them have been definitively proven. The information paradox remains one of the most significant mysteries in theoretical physics, highlighting the need for a unified theory that can reconcile general relativity and quantum mechanics. Understanding the fate of information in black holes could unlock new insights into the nature of the universe and the fundamental laws that govern it. As scientists continue to investigate, the information paradox serves as a compelling reminder of the enigmatic and puzzling nature of black holes, challenging our deepest assumptions about reality and pushing the boundaries of human knowledge. The 10th unknown involves the potential connection between black holes and dark matter. Imagine for a moment that these two cosmic mysteries, black holes and dark matter, could be intricately linked. Dark matter is an elusive substance that makes up about 27% of the universe, yet it doesn't emit, absorb, or reflect light, making it invisible to current instruments. Despite its invisibility, we know it's there because of its gravitational effects on galaxies and galaxy clusters. Now, what if black holes could provide clues about the nature of dark matter? One intriguing theory suggests that dark matter could be made up of primordial black holes. These are black holes that formed in the early moments after the Big Bang, long before stars and galaxies took shape. If true, these primordial black holes could make up a significant portion of dark matter, explaining the unseen mass influencing the cosmos. Scientists are delving into this possibility by studying the gravitational effects of black holes on their surroundings. For instance, if primordial black holes are indeed a major component of dark matter, their gravitational influence might be detected in the way galaxies rotate or in the bending of light from distant stars, a phenomenon known as gravitational lensing. Another captivating idea is that the interactions between black holes and dark matter could reveal new physics. For example, if dark matter particles are annihilated near a black hole, they might produce detectable signals like gamma rays. Observing such emissions could provide indirect evidence of both dark matter and primordial black holes. However, it's important to note that these ideas are still highly speculative. The nature of dark matter remains one of the most profound mysteries in cosmology, and the connection to black holes is far from proven. Yet, the potential link between these two enigmatic entities tantalizes scientists, offering a fascinating avenue for research. If future observations and experiments can confirm a relationship between black holes and dark matter, it would revolutionize our understanding of the universe, shedding light on two of its most perplexing components. Until then, the quest to uncover the secrets of black holes and dark matter continues, driving the pursuit of knowledge to the very edges of what we know about the cosmos. The 11th unknown involves whether black holes can merge. Imagine two black holes drifting through the cosmos, each with its own immense gravitational pull. Eventually, their paths cross and they start to spiral towards each other in a dance of destruction and creation. This cosmic collision is not just a violent event but a transformative one, where two black holes merge to form a single, larger black hole. When two black holes collide, they produce ripples in the fabric of space-time called gravitational waves. These waves travel across the universe, carrying information about the cataclysmic event. In 2015, scientists made history by detecting these gravitational waves for the first time, confirming a major prediction of Einstein's theory of general relativity. The event was a collision of two black holes, and it marked the beginning of a new era in astrophysics. As the black holes spiral closer, their immense gravitational forces warp space-time in a phenomenon known as the inspiral phase. During this phase, they lose energy through the emission of gravitational waves, causing them to draw even closer together. As they merge, the energy released in the form of gravitational waves is so powerful that it can exceed the combined energy output of all the stars in the observable universe. This final phase, called the ring-down phase, sees the newly formed black hole settling into a stable state. The merged black hole is typically larger and spins more rapidly than either of the original black holes. Interestingly, the process of black hole merger also provides insights into the properties of black holes themselves, such as their masses, spins, and the nature of the gravitational waves they emit. Observing these collisions helps scientists test the limits of general relativity and explore the behavior of gravity under extreme conditions. One of the most fascinating aspects of black hole mergers is how they contribute to the growth and evolution of black holes over time. Mergers allow black holes to gain mass, grow larger, and possibly become the supermassive black holes found at the centers of galaxies. These mergers also offer a unique way to study the universe's expansion and the distribution of matter throughout the cosmos. As we continue to develop more sensitive instruments to detect gravitational waves, we will undoubtedly learn more about these dramatic and energetic events. The ability to observe black hole mergers opens a new window into the universe, allowing us to witness some of the most powerful processes that shape our cosmic landscape. The question of whether black holes can merge is no longer theoretical. It is a proven phenomenon that continues to unravel the mysteries of the universe and expand our understanding of these enigmatic cosmic giants. The 12th unknown involves the sound of black holes. Imagine a place in the universe so mysterious that it not only warps light and time but also emits sound waves. Yes, you heard that right, sound waves. This notion might seem like science fiction, but it's rooted in fascinating discoveries. In 2003, scientists using NASA's Chandra X-ray Observatory made an astonishing find. The Perseus galaxy cluster had a supermassive black hole at its center emitting sound waves. These sound waves traveled through the hot gas surrounding the black hole, creating ripples that could be translated into a cosmic melody. Now, you might be wondering how sound can exist in the vacuum of space. While space itself is mostly a void, there's enough gas in galaxy clusters to carry sound waves, albeit at frequencies much lower than what the human ear can detect. The sound waves emitted by the black hole in the Perseus cluster were measured at a pitch 57 octaves below middle C, far beyond the range of human hearing. To put this into perspective, it's a B-flat note but so low that it vibrates once every 10 million years. The discovery of sound waves in black holes adds another layer to our understanding of these enigmatic objects. It's not just the visual and gravitational effects that intrigue scientists, but also the auditory signals that offer new insights. By studying these sound waves, researchers can learn more about the behavior of black holes and the environments around them. In essence, sound waves act as a form of black hole communication, revealing details about their activity and the surrounding gas. This acoustic phenomenon also ties into the larger question of how black holes influence their cosmic neighborhoods. The sound waves from the Perseus black hole, for example, have been found to help regulate the temperature of the gas in the galaxy cluster, preventing it from cooling too rapidly and forming stars at an accelerated rate. This shows that black holes, through their sound waves, play a crucial role in the cosmic balance. Despite these groundbreaking findings, the study of black hole sound waves is still in its infancy. Scientists are eager to explore further, using advanced telescopes and instruments to detect and analyze these low-frequency waves in other galaxy clusters. The idea that black holes sing, albeit in tones we cannot hear, adds a poetic dimension to their enigmatic presence in the universe. It reminds us that there are many more layers to these cosmic giants waiting to be discovered. The sound of black holes challenges our perceptions and expands our understanding, proving once again that the universe is full of wonders beyond our wildest imagination. The 13th unknown involves the possibility of black holes being wormholes. Picture black holes not as endpoints but as bridges to other places in the universe or even to entirely different universes. This captivating idea comes from the realm of theoretical physics, particularly from the concept of wormholes. In essence, a wormhole is a tunnel through space-time that connects two distant points. Think of it like a shortcut where instead of traveling from one side of the universe to the other the long way, you could take a direct path through the wormhole. The idea of black holes being wormholes stems from the equations of Einstein's theory of general relativity. According to this theory, the intense gravitational forces of a black hole could warp space-time to such an extent that it forms a tunnel, with the black hole serving as the entrance on one side and a hypothetical white hole acting as the exit on the other. This white hole, though purely theoretical, would be a region where matter and energy are expelled rather than consumed. Some scientists hypothesize that these black hole wormholes could connect not just different points in our universe, but also other universes in a multiverse scenario. Imagine being able to travel to a parallel universe with different laws of physics and a distinct version of reality. This idea has captured the imagination of both scientists and science fiction writers alike. However, there are significant challenges to this concept. One major issue is the stability of a wormhole. Theoretical models suggest that wormholes might be inherently unstable and could collapse almost instantly after forming. To remain open, a wormhole would require a form of exotic matter with negative energy density, something that has yet to be discovered or created. Another challenge is that even if stable wormholes existed, traveling through one could be incredibly dangerous due to the extreme gravitational forces involved. These forces could potentially destroy any matter attempting to pass through, making the journey perilous at best. Despite these obstacles, the possibility of black holes as wormholes continues to intrigue researchers. If we could find even indirect evidence of such phenomena, it would revolutionize our understanding of space, time, and the very fabric of the universe. For now, the idea remains a tantalizing yet speculative frontier in astrophysics, a reminder of the boundless possibilities that lie beyond our current knowledge. The concept of black holes as wormholes pushes the limits of our imagination, urging us to dream big and explore the mysteries of the cosmos with even greater curiosity. The 14th unknown involves how black holes influence their surroundings. Picture a black hole not just as a distant, isolated entity, but as a force that profoundly affects everything around it. One of the most dramatic ways black holes influence their surroundings is through their immense gravitational pull. This gravitational force can draw in nearby stars and planets, causing them to orbit the black hole in a dance of cosmic proportions. When a star strays too close to a black hole, it can be torn apart in a process known as tidal disruption. The powerful gravity stretches and compresses the star, ripping it into a stream of gas that spirals into the black hole, creating a spectacular light show known as an accretion disk. This disk glows brightly as the material heats up, emitting X-rays and sometimes even visible light. Another way black holes impact their surroundings is by emitting jets of high-energy particles. These jets, which can extend for thousands of light years, are launched from the regions around the black hole where magnetic fields twist and accelerate particles to near light speed. These powerful jets can influence star formation in the galaxy by compressing gas clouds, potentially triggering new stars to form, or they can heat the gas, preventing it from collapsing into new stars. Black holes can also affect the motion and behavior of stars in their vicinity. In the center of our Milky Way galaxy, for instance, hundreds of stars orbit the supermassive black hole Sagittarius A. These stars move at incredibly high speeds, their paths dictated by the black hole's massive gravitational influence. By studying these stellar orbits, scientists can learn more about the black hole's properties, such as its mass and spin. Moreover, black holes can play a role in shaping planetary systems. While the intense gravity of a black hole is typically considered a force of destruction, some theories suggest that during the chaotic early stages of galaxy formation, black holes might help stabilize the orbits of planets around their stars. Even though the idea seems counterintuitive, it's a reminder of the complex and often surprising ways black holes can interact with their cosmic environments. Despite these fascinating interactions, much about how black holes influence their surroundings remains a mystery. Scientists are continually observing and modeling these processes to gain a deeper understanding. The profound impact of black holes on nearby stars and planets highlights their role as both destroyers and creators in the cosmic theater. As we delve deeper into the study of black holes, we uncover more about the dynamic and interconnected nature of the universe, where even the most extreme objects can have far-reaching effects on their celestial neighbors. The 15th unknown involves the first photograph of a black hole. In 2019, humanity achieved a historic milestone by capturing the first ever image of a black hole, thanks to the Event Horizon telescope. This groundbreaking achievement marked a significant leap in our understanding of these cosmic behemoths. The black hole imaged is located in the center of the Messier 87 galaxy, about 55 million light-years from Earth. What we see in the photograph is a dark central region, which is the shadow of the black hole, surrounded by a bright ring of light. This light is from superheated gas and dust spiraling into the black hole at incredible speeds. The photograph, often compared to a glowing donut, is not just a triumph of technology and teamwork, but also a visual confirmation of Einstein's theory of general relativity. Capturing this image required an unprecedented global collaboration, with 8 ground-based radio telescopes across the world working in unison. The data collected was so immense that it had to be stored on hundreds of hard drives and physically flown to a central location for processing. The image was then painstakingly constructed from this data, representing years of effort by an international team of scientists. This first photograph of a black hole is more than just a visual marvel. It has profound scientific implications. It provides direct evidence of the existence of event horizons, the point beyond which nothing can escape a black hole's gravitational pull. It also opens up new avenues for testing our understanding of gravity and the behavior of matter in extreme environments. The photograph has spurred new research and observations, helping scientists to refine their models and theories about black holes. It has also inspired the public, bringing the mystery and wonder of these cosmic objects to a broader audience. The significance of this achievement cannot be overstated. It represents a new era in astrophysics, where we can now directly observe and study the very edges of black holes, pushing the boundaries of what we know about the universe. As technology advances, future observations will undoubtedly provide even sharper images and deeper insights, unraveling more of the mysteries that black holes hold. This first photograph is a testament to human ingenuity and curiosity, reminding us that even the most daunting challenges can be overcome with determination and collaboration. It stands as a beacon of scientific achievement, illuminating the path to future discoveries and a deeper understanding of the cosmos. The 16th unknown involves whether we can harness energy from black holes. Imagine tapping into one of the most powerful forces in the universe to generate energy, effectively turning black holes into cosmic power plants. This speculative idea is rooted in the concept of extracting energy from the rotational motion of a spinning black hole, a process known as the Penrose process. Proposed by physicist Roger Penrose in 1969, this process suggests that if you could drop an object into the region outside the event horizon, known as the ergosphere, it could theoretically split into two. One part would fall into the black hole, while the other would escape, carrying more energy than the original object. This surplus energy could then be harnessed, providing a new source of power. Another fascinating idea is the concept of Hawking radiation. As we discussed earlier, black holes are thought to emit radiation due to quantum effects near the event horizon. If it were possible to capture this radiation, it could serve as a form of energy extraction, albeit at a very slow rate due to the faintness of Hawking radiation. This would require advanced technology far beyond our current capabilities, but it opens up intriguing possibilities for the future. Additionally, there's the notion of using black hole accretion disks as energy sources. These disks are composed of superheated gas and dust spiraling into the black hole, emitting vast amounts of electromagnetic radiation, particularly X-rays. If we could devise a method to capture this radiation efficiently, it could be converted into usable energy. Theoretical constructs like Dyson spheres, which are hypothetical megastructures built around a star to capture its energy, could be adapted to black holes, potentially providing an almost limitless supply of energy. However, harnessing energy from black holes poses enormous technical and ethical challenges. The immense gravitational forces, extreme radiation, and the sheer distance of most black holes from Earth make it a daunting task. Additionally, the ethical implications of using such powerful and potentially dangerous sources of energy would need careful consideration. Despite these challenges, the prospect of tapping into the energy of black holes continues to captivate scientists and futurists alike. It represents the ultimate frontier in energy generation, pushing the boundaries of what we consider possible. As our understanding of black holes deepens and technology advances, we may one day unlock the secrets of these cosmic giants, turning them into powerful allies in our quest for sustainable energy. Until then, the idea of harnessing energy from black holes remains one of the most speculative yet exciting unknowns in the study of black holes, challenging us to think beyond the limits of our current knowledge and imagine the incredible possibilities of the future. The 17th unknown involves whether there are black holes in our own galaxy. The Milky Way, our home galaxy, is a vast cosmic arena teeming with stars, planets, and other fascinating celestial objects. Among these are black holes, both known and potentially undiscovered. The most prominent black hole in our galaxy is the supermassive black hole located at its center, known as Sagittarius A, situated about 25,000 light-years from Earth. This colossal black hole has a mass equivalent to about 4 million suns and plays a crucial role in the dynamics of our galaxy. Observations of stars orbiting close to Sagittarius have provided compelling evidence of its existence, showcasing the immense gravitational forces it exerts. In addition to this supermassive black hole, the Milky Way is believed to host many smaller stellar mass black holes. These smaller black holes form when massive stars, much larger than our Sun, exhaust their nuclear fuel and collapse under their own gravity. Estimates suggest that there could be millions of such stellar mass black holes scattered throughout our galaxy, yet detecting them is incredibly challenging due to their dark and elusive nature. Most of the known stellar mass black holes have been identified through their interactions with companion stars in binary systems. When a black hole accretes matter from a nearby star, the material heats up and emits powerful X-rays which can be detected by telescopes. One famous example is the black hole in the binary system Cygnus X1, located about 6,000 light-years from Earth. This black hole, with a mass about 15 times that of our Sun, was one of the first to be discovered and has been extensively studied. However, many black holes in the Milky Way remain hidden without companion stars to reveal their presence. Scientists are continually developing new methods to find these elusive objects, such as searching for the gravitational effects they exert on nearby stars and gas clouds or detecting the faint radiation they emit. Advanced instruments like the Laser Interferometer Gravitational Wave Observatory, which has detected gravitational waves from black hole mergers, also offer promising avenues for discovering hidden black holes in our galaxy. The possibility of undiscovered black holes in the Milky Way adds an element of mystery and excitement to our understanding of the cosmos. These hidden giants could help us learn more about the formation and evolution of black holes, as well as their impact on the structure and dynamics of our galaxy. As our detection capabilities improve, we may uncover many more black holes lurking in the dark corners of the Milky Way, further enriching our knowledge of these fascinating cosmic enigmas. The 18th unknown involves the evolution of black holes over time. Imagine a black hole not as a static entity but as a dynamic object that grows and changes over billions of years. Black holes evolve through a complex interplay of growth and interaction with their surroundings. Initially, a black hole forms from the collapse of a massive star, creating a stellar mass black hole. From this point, black holes can grow in size through a process known as accretion, where they pull in gas, dust, and other material from their environment. This process leads to the formation of an accretion disk around the black hole, where matter is heated to extreme temperatures as it spirals in, emitting intense radiation. Over millions to billions of years, black holes can also grow by merging with other black holes. These mergers are dramatic events that produce powerful gravitational waves rippling across the universe. Each merger results in a more massive black hole, contributing to the growth of supermassive black holes found at the centers of galaxies. Additionally, black holes can interact with stars, tearing them apart in tidal disruption events, which also contributes to their growth. As black holes evolve, their spin rates can change. Initially, a black hole may have a rapid spin, but as it accretes matter, it can either spin faster or slower depending on the direction of the inflowing material. The spin of a black hole influences the behavior of the accretion disk and the formation of relativistic jets that can extend thousands of light years into space. Over cosmic timescales, black holes can affect the evolution of their host galaxies. The energy released by accreting black holes, particularly in the form of jets and radiation, can regulate star formation by heating and expelling gas, shaping the growth and structure of galaxies. This feedback mechanism creates a dynamic relationship between black holes and their cosmic environments. Despite these insights, much about the long-term evolution of black holes remains uncertain. Scientists are continually studying black holes using advanced telescopes and simulations to uncover more about their growth and changes over time. The evolution of black holes over billions of years reflects the intricate and ever-changing nature of the universe, where even the most mysterious objects are in constant flux. As we deepen our understanding of black hole evolution, we gain a richer appreciation for the complex processes that shape the cosmos and the enigmatic forces at play. The 19th unknown involves black holes and time travel. Imagine using a black hole not just as a cosmic phenomenon to observe, but as a potential gateway for time travel. This idea has long sparked the imagination of scientists and science fiction writers alike. One of the most tantalizing theories comes from Einstein's general relativity, which suggests that the intense gravitational fields around black holes can warp space-time to such an extent that they could potentially create a bridge to different points in time. In this scenario, a black hole could connect to a white hole, forming a tunnel known as a wormhole. If such a wormhole existed and remained stable, it could theoretically allow travel not only through space but also through time. Imagine entering a black hole and emerging in the distant past or future. Such a possibility opens up a realm of sci-fi scenarios where explorers could witness historical events firsthand or venture into unknown futures. Movies and books often depict these journeys with varying degrees of scientific accuracy, adding elements of adventure and intrigue to the concept. However, the practicalities of time travel through black holes are fraught with challenges. One major issue is the stability of wormholes. Theoretical models suggest they might be inherently unstable, collapsing almost instantly. To keep a wormhole open, it would require exotic matter with negative energy density, which we have yet to discover. Another challenge is the immense tidal forces near a black hole, which could stretch and compress any object passing through, a process known as spaghettification. Despite these challenges, the allure of time travel continues to captivate us. Some theories even suggest that if you could navigate the singularity within a black hole safely, you might exit at a different time, essentially experiencing a form of time travel. While this remains speculative, it fuels our curiosity and drives scientific inquiry. Scientists are continually exploring these concepts, using advanced simulations and observations to probe the nature of black holes and their potential as cosmic time machines. Though actual time travel remains a distant dream, the idea that black holes could one day unlock the secrets of time challenges us to push the boundaries of our understanding and imagine the extraordinary possibilities that lie within the universe. The 20th unknown involves future discoveries about black holes. As we continue to push the boundaries of scientific knowledge and technological innovation, the mysteries of black holes beckon us with the promise of unimaginable discoveries. Future advancements in technology and research could unlock secrets that we can barely conceive today. Imagine telescopes with the ability to peer deeper into the cosmos, providing unprecedented clarity and detail of black holes and their surrounding environments. Advanced space missions could deploy probes capable of venturing closer to black holes than ever before, equipped with instruments that can withstand the extreme conditions near these cosmic giants. These probes might collect data on the event horizon, the accretion disk, and potentially even the elusive singularity itself. One exciting avenue of future research is the development of quantum theories of gravity, which aim to unify general relativity and quantum mechanics. Such theories could provide a deeper understanding of the fundamental nature of black holes, shedding light on the enigmatic singularity and resolving the black hole information paradox. We might discover how information is truly preserved in these gravitational behemoths, revolutionizing our understanding of the universe. Additionally, the detection and study of gravitational waves will likely continue to yield groundbreaking insights. More sensitive instruments and detectors could reveal a greater number of black hole mergers, allowing scientists to map the population of black holes in the universe with greater precision. These observations could help us trace the evolution of black holes over cosmic timescales and understand their role in galaxy formation. Artificial intelligence and machine learning will play a crucial role in future black hole research. These technologies can analyze vast amounts of data from telescopes and simulations, identifying patterns and making predictions that would be impossible for humans to discern alone. AI could help us discover new black holes, predict their behavior, and even simulate their environments with remarkable accuracy. The exploration of black holes may also lead to practical applications that we can scarcely imagine today. For instance, understanding the mechanisms of black hole accretion could inspire new ways to harness energy on Earth, while insights into the warping of space-time might pave the way for breakthroughs in space travel and communication. As our technological capabilities grow, so too will our ability to uncover the secrets of black holes. The potential discoveries are as vast and mysterious as the black holes themselves, from deeper insights into the nature of gravity and quantum mechanics to the possibility of new, uncharted realms of the universe. The quest to unravel the mysteries of black holes will continue to inspire and challenge us, driving humanity to explore the outer edges of knowledge and imagination. The future of black hole research promises to be a thrilling journey, one that will undoubtedly expand our understanding of the cosmos and our place within it. So, as we gaze into the depths of the universe, the question remains, what will we discover next? Stay tuned, because the adventure is just beginning. The journey into the enigmatic world of black holes has revealed 20 mind-boggling unknowns that challenge our understanding of the cosmos. First, we explored the true nature of singularity, that infinitely dense point where physics as we know it breaks down. Next, we dove into what happens beyond the event horizon, the point of no return where time and space are warped. We then entertained the possibility that black holes could lead to other universes, acting as cosmic gateways in the multiverse. Moving on, we pondered the origin of supermassive black holes, those colossal giants at galaxy centers, and examined their role in galaxy formation, possibly acting as cosmic architects. The notion that black holes might evaporate over time via Hawking radiation added another twist to our understanding. We also speculated about mini black holes, tiny but powerful remnants from the early universe. The concept of time dilation near black holes, where time slows dramatically, opened up yet another fascinating aspect. The information paradox questioned whether information is truly lost in black holes, a puzzle that pits general relativity against quantum mechanics. The potential connection between black holes and dark matter suggested that primordial black holes might make up this mysterious substance. We confirmed that black holes can indeed merge, producing gravitational waves that ripple through the universe. The sound of black holes emitting low-frequency waves added an almost poetic dimension to their presence. The possibility of black holes being wormholes ignited imaginations, suggesting journeys to other parts of the universe or even different universes. We also explored how black holes influence their surroundings, from tearing apart stars to shaping galaxies with their jets. Capturing the first photograph of a black hole marked a historic milestone, providing visual confirmation of these cosmic giants. We speculated on harnessing energy from black holes, perhaps turning them into cosmic power plants. Knowing that black holes exist in our own Milky Way galaxy reminded us that these mysterious objects are closer than we might think. The evolution of black holes over billions of years showed us how these entities grow and change, influencing their cosmic neighborhoods. The idea of black holes as potential gateways for time travel captivated our imaginations even as we acknowledged the challenges. Finally, we looked toward the future, anticipating groundbreaking discoveries that will further unravel the mysteries of black holes. From deeper insights into their fundamental nature to practical applications we can scarcely imagine. This recap of the 20 unknowns not only highlights the profound mysteries surrounding black holes, but also underscores the relentless curiosity and ingenuity driving our quest to understand the universe. Stay tuned as we continue this awe-inspiring journey into the unknown. Now that we've explored these incredible mysteries, it's your turn to dive in. What questions do you have about black holes? Maybe there's a theory you've been pondering or a mind-boggling idea that you'd like to share. We want to hear from you. Leave your thoughts, questions, and theories in the comments below. Let's get a conversation started about the wonders of black holes and the universe. Your curiosity and insights can spark new discussions and maybe even inspire future videos. So don't be shy, join the cosmic conversation and let's explore the unknown together. Also, if you enjoyed this journey into the mysteries of black holes, don't forget to like this video and subscribe to our channel. Hit the notification bell so you never miss an update on our latest space explorations. Thanks for watching and keep looking up at the stars with wonder. In summary, our journey into the mysterious realm of black holes has unveiled some of the most captivating enigmas of the universe. From the singularity at their core to the possibility of them being passageways to other dimensions, black holes stretch our imagination and challenge our understanding of physics. We've delved into their role in galaxy formation, the concept of Hawking radiation, the speculative existence of mini black holes, and the mind-bending idea of time dilation near these cosmic giants. We've pondered the information paradox and the potential link between black holes and dark matter. We've confirmed their ability to merge, creating gravitational waves, and even explored the poetic notion of black holes emitting sound. The idea of black holes as wormholes and their profound influence on their surroundings adds another layer of fascination. The historic capture of a black hole's image and the speculative thoughts on harnessing their energy remind us of the immense power and mystery they hold. Knowing that black holes are not just distant phenomena but also exist in our Milky Way brings them closer to home. As we look to the future, the promise of new discoveries keeps our curiosity alive. So, what's next on our cosmic journey? Stay tuned as we explore other space mysteries, from the enigmatic dark matter to the possibility of life on exoplanets. Thank you for joining us on this incredible journey into the unknown. If you enjoyed this deep dive into the mysteries of black holes, please give this video a thumbs up, subscribe to our channel, and hit that notification bell to stay updated with our latest adventures in space exploration. We can't wait to delve into more fascinating topics with you. Remember to leave your questions and theories in the comments below. We love hearing from you. Until next time, keep looking up at the stars with a sense of wonder and curiosity.